I'd like to work on some of the practice free response questions for the Kinetics packet with you. I'm not sure how many questions I'll try to do in a video. I don't want them to get too terribly long, but try to work through the first couple of questions in your packet at least. The questions that are here are classified as essay questions. Back in the day of the AP exam earlier on, there used to be sort of more of a division between essay type questions and more calculation or problem-based questions that had more mathematics required in them. Here we just kind of group them all together as free response questions. So don't worry too much about that heading. The answers are still best completed with as few words as possible, but with a complete thought and without taking any shortcuts that get you into trouble in terms of your answer maybe being misleading or incomplete or not showing enough of your understanding. So we'll work on some of these free response questions anyway, a couple at a time in a video, and we'll see how time looks. And then we'll kind of cut them off and make them reasonable in length so you can kind of get through as many of them as possible without having to sit through too much of a video. So in this first question, I've taken away part of the problem. The first part of this, part A, is actually sort of a question that is no longer part of the content of the curriculum from this year. So it's been somewhat trimmed down. In fact, as a result of that, this first reaction equation here, actually, I should have taken out, goes with part A. So we actually don't need that for the part that we're going to answer here in part B. So the question's asking or telling us that the following data give the pressure of A as a function of time, and we're obtaining 100 degrees Celsius for the reaction. We haven't seen data where we have pressure and time. It's typically, we talk about molarity in time. But the good news is, or like, if it's good news, but the clarification I want to start out with here is that pressure is proportional to molarity. Pressure can be used the same way that molarity can be used in terms of graphing these or coming up with graphs to determine the rate order or understand more about the reaction rate order from graphs. And so when we see pressure here, we can treat that as molarity, and that's not just a magic trick that we're pulling there. If we think about PV equals nRT as our ideal gas law, and we get pressure by itself, we would end up with pressure equals moles times RT over volume. And if we look at that closely, then pressure here on the left side of the equation will be proportional to this moles over volume, which is molarity. So pressure is proportional, okay, to molarity, moles over liters, or moles per liter. And so as molarity increases, pressure would increase exactly proportionally, where R and T are more or less held constant here. R we know is a constant, and T is a temperature that they set at 100 degrees Celsius in this problem, or 373 Kelvin. So those aren't really part of our consideration. But pressure and molarity are proportional, and so for that reason, if you're given data with molarity in time or pressure in time, we can actually treat it exactly the same and graph things on our y-axis using pressure the same way that we would graph them using molarity on that y-axis. So that's really helpful. And it's important to remember that it's not a parlor trick that they're pulling on you when they give you pressure. It's directly proportional to molarity. It's measuring something a little differently, but it's proportional to molarity, and so it can be substituted into those graphs. And so the question's asking, describe without any calculations how graphs could be used. This is sort of one of those more modern questions where it'll tell you to answer something but not actually show any calculations, or maybe not even give you any numbers that would allow you to do calculations. But they've narrowed it down for us, which is kind of nice. They say, how could you tell whether it's first or second order? So in other words, we know it's not zero order, is the sort of assumption we can make. But keep in mind, what does that mean, first and second order? So remember the order of our graphs, our typical graphs, we have three choices. When it's a zero order graph, we have concentration or molarity or pressure versus time for zero order. For first order, we have natural log of concentration or pressure versus time. So that's first order. And then for second order, we have reciprocal or 1 over pressure or molarity versus time. So this is second order. So zeroth order or zero order, I don't like zeroth order, but that's what they call it. First order and second order graphed as concentration or pressure, natural log of concentration or pressure, and then reciprocal of concentration or pressure. So they've already kind of helped us by getting rid of this one. It's first or second order. So how would we know if it's first order or second order with respect to the pressure of A? Well, the way we would do that is, in describing it without any calculations, we would graph, right, the natural log of the pressure of A versus time, and we would graph the reciprocal, 1 over the pressure of A versus time, and see which graph gives us a linear fit. for the best fit curve, or for the line of best fit. And that's the idea. Remember, we're looking for the one that has that linear fit. So if you plot all these points on a graph, and we actually have the calculation or the calculator or a spreadsheet or even just our eyeball with a ruler or a straight edge, draw in and try to draw in a line of best fit, which one's linear? And the idea is that just one of those would actually be linear. Okay. The one that's linear is going to tell us whether it's first or second order. So if natural log of pressure versus time is linear, then the reaction is, we would say that the reaction, is first order with respect to A. And then if reciprocal, 1 over pressure of A versus time is linear, then we'd be looking at a second order. Reaction would be second order. And remember, it can't be both. One or the other in this case would be the correct order for A. And the only way we can graph this and determine this is for A, because it's the only thing we have data for. So even though this reaction uses A, produces B, produces C, the only data that we have is to determine the order with respect to A. And since that's the only reactant in this equation, that just makes sense anyway. So which one of those it would be based on that. So that's kind of answering the first question. Determine whether this reaction is first or second order. We've described how we would do that. And then how would we determine the rate constant? Remember, the rate constant, K, is found as the absolute value of the slope. Let's try that again. Absolute value of the slope for the graph with the linear fit. So if we had a linear fit on our first order graph, then we would expect to see that we'd have sort of a linear graph sort of like that, and we would just find the slope of this line. And of course, in this case, right, this would obviously have a negative slope. This would have a negative slope. And to find K is never a negative value. The rate constant is always a positive value. So we would need to take the absolute value of that negative slope for this graph if that were the linear one. If reciprocal of pressure versus time was linear, it would actually be a straight, a linear line. It would be a line showing a positive slope. So in that case, you wouldn't actually have to have the absolute value is quite as vital. But just to make it consistent, whichever one of these two graphs was linear would tell us the order, and then we would take the absolute value of the slope of that linear fit line from whichever graph that it came from. And that absolute value of slope would give us K. And that's true for whichever order we're talking about, 0 order, first order, or second order. The absolute value of the slope on the graph showing linear fit will always be equal to K. And then the units would kind of come from there. It didn't ask us anything about units. The units would be a little different depending on whether it was a first order or second order graph that was the linear graph. So that's our answer for that one. All right, let's look at the next question. Question 2 gets us to another reaction, a pretty simple reaction, PCl3 and Cl2 forming PCl5. And notice here, it gives us some really important context. Don't blow past the prompt. You see the equation. Oh, there's an equation. What's the first question? Suppose that 2 moles. No, don't do that. Take a look at the sentence in between, because there's some really important information in there. The forward reaction is first order for both PCl3 and Cl2. That's vitally important. And the reverse reaction is first order for PCl5. So we get first order all around. If we didn't read that first sentence, we might be hunting around for, oh, they didn't give me enough information to answer this question. How the heck am I supposed to do it? Well, it's there. You just have to know what you're looking for, right? So let's take a look at part A, where it says that suppose now that 2 moles of PCl3 and 1 mole of Cl2, so we're getting 2 moles of this and 1 mole of this, are mixed in a closed container at constant temperature. Now you might imagine this sort of as a rice table. Thinking about this as a rice table, the amount of PCl3 would decrease with time, the amount of Cl2 would decrease with time, the amount of PCl5 would have to increase because there isn't any PCl5 in there at the beginning, right? So if we were thinking about this in a rice table, we would expect that this amount would decrease, this amount would decrease, and this amount would increase. Got to get a little closer to that reaction. There's not a ton of space here for me to write with the text for that prompt coming right in below, but this one's going to increase, and those signs are really important because we want to think about those in terms of a rice table, which really isn't vital in this question because we're not doing an equilibrium calculation. But it is going to help us understand the graph that they want us to draw. So we need to know that PCl3 and Cl2 would both decrease in amount, and PCl5 would increase in amount. And further than that, we can recognize that this is a 1-to-1-to-1 reaction. So they'll all change by the same amounts. In other words, if I was going to fill this in as a rice table, I would say this is going to decrease by x, and this is going to decrease by x, and this is going to increase by x because it's a 1-to-1-to-1 ratio in the balanced equation. That's important as well in understanding how we're going to draw the graph that they ask for in part A. Draw a graph that shows how the concentrations of the three participants here will change with time until after equilibrium has been firmly established. So our graph, as always, our XY graph here, is going to be concentration. So concentration of each of our species, and then time down here. We don't really need numbers per se on the timeline for sure. We don't know when equilibrium will be established. We just know that as time passes, eventually we'll have equilibrium. But we do want to kind of think about some sort of numbers on the y-axis. And so for PCl3, it says we start out with 2 moles. So I'm going to say that this is 1, this is 2. And we can say that as concentration, we could say that as moles. Because we don't really have a volume for the container that it's in. We don't really know what the concentration is. We could say it's a 1 liter container, and then 2 moles for every 1 liter, and 1 mole for every 1 liter. So whether that's molarity or moles, it's going to start out as 2 for PCl3. And then I'm going to draw that in from here on forward. I'm going to use red for that. So PCl3 in my graph is going to be in red. Actually, better go with solid. Let's say using it as solid. And then Cl2 I'm going to use as a dashed line. Okay. And then PCl5, we'll try to maybe do as dots. Okay, so we have different textures to our line. That's kind of important to do because on a test you would have just a pencil typically, and we wouldn't want to have to get used to using too many colors on our graphs or other drawings that we would do. So PCl3 starts at 2, and then it's going to decrease. Cl2 is going to start here at 1, is going to decrease. PCl5 starts at 0, right? There isn't any of that to start out with. And what's going to happen to those amounts with time? Well, if I start out here with PCl3, it's going to decrease with time. And it's going to decrease more rapidly at first because there are more collisions when there are more particles. And then as some of the PCl3 is used up and some of the Cl2 is also used up, both of those will be fewer and fewer particles present and fewer collisions. So the reaction rate will be fastest at first, and then it will gradually slow down and eventually level off. And the amount of the amount of PCl3 and Cl2 present will eventually level off. The reaction rate will kind of reach a fixed rate as well. It won't ever become a 0 rate, but it will kind of level off in terms of how slow it's going to get. So PCl3 is going to start out at 2, and it's going to decrease with time until it levels off. Let's say here. Okay. Actually, I better not go down quite that much, and you'll see why here in just a minute. So it's going to go down by some amount, and then it's going to level off. Cl2, remember, according to my little graph or my little rice table, or my pseudo rice table, Cl2 is going to decrease by the same amount over time. And so these lines will actually be parallel with each other because the Cl2 line is going to decrease in the same way. As PCl3 is used, Cl2 is used at the same rate, 1 particle for every 1 particle. And so Cl2 will decrease in a very parallel track. We can see how much each of those went down is about the same the way that I've drawn it here. And then PCl3 will increase, and it'll increase at the same rate as well, because remember, they're all related as that 1-to-1-to-1 ratio. And so what we need to do is draw PCl3's concentration increasing, most rapidly at first, and then leveling off, eventually as equilibrium is reached. But it's going to sort of mirror the picture that we have here so far. So if I try to mirror that curve, except upside down, I end up with kind of a graph that looks kind of like this. It's going to kind of level off around the same time. And again, my graph here, the points are kind of hard to distinguish maybe between dashes and short dots. So maybe I want to label this. Here's my PCl3. This bottom one was my Cl2. And then my PCl5 was produced here in the middle. And so as PCl3 and Cl2 are both used, their amounts will decrease as the reaction continues to reach toward reaching equilibrium. PCl5, there isn't any of that to start with. It'll increase as we reach it until we reach equilibrium, and then it will level off. So if we have to kind of identify here, like whenabouts was equilibrium reached, it's when all three have kind of leveled off. So probably somewhere kind of right in here, and from any point afterwards, this would represent on my graph the point at which equilibrium was reached, and this is the sort of stage right in through here. Until some other disturbance comes along, this would be the equilibrium condition. And those lines would just stay flat. Now again, remember, equilibrium doesn't mean the reaction has stopped. It just means that PCl3 and Cl2 are being consumed at the same rate at which PCl5 is being made. And so the two reactions, forward and reverse, are essentially canceling each other's progress out, and we're seeing no net change in how much of each of those is present. Also important to remember when you're drawing a graph like this, when they want you to show equilibrium being established, we don't ever get anything to reach zero. Nothing reaches zero. So we don't get PCl3 completely used. We don't get Cl2 completely used, because equilibrium means we're always going to have all of the particles present in the equilibrium. And that's going to help us to remember that it's a dynamic condition, that nothing ran out, there isn't a limiting reactant. It's just that we continue on at equilibrium where there's no overall net change. So for the rate law for the forward reaction, that's where that sentence that I mentioned is really important is important again, because it tells us that the forward reaction is first order with respect to PCl3 and Cl2. So if I'm answering B, I'm going to write my rate law as rate equals K times the concentration of each of those parts to the first order. So PCl3, first order, Cl2, first order. And you don't have to put those ones up there, but they're implied, but it is first order with respect to both. All right, so that's our forward K. Sometimes you'll see that written, just so you know, sometimes you might see it written as rate forward and then K forward. They do sometimes put little F's in there behind the rate and behind the rate constant to imply the forward versus the reverse, especially if this was a problem where they were asking you to then also write an expression or use an expression for the reverse reaction. We want to be able to distinguish that those rates are considered separately and they can potentially be different. The K value, the rate constant, can be different, even if we're talking about equilibrium when they're kind of the same rates. You should recognize that there are conditions at which, or situations where the forward and reverse rates, the constants would be different, and the units on them would be different as well. So C says provide a molecular explanation for the dependence of the rate on forward reaction on concentrations of the reactants. When you hear that kind of prompt, provide a molecular explanation, that's a good kind of code phrase that says make sure you're talking about collisions. Make sure you're talking about particles and their collisions when it comes to the rate of a reaction, or how something influences the rate of a reaction. Collisions. And part D, again, provide a molecular explanation. Make sure you're talking about particles and collisions. Vitally important, especially on a question that we can recognize has a lot to do with kinetics, because kinetics is all about the motion and collisions of particles and how we can recognize it in mathematical ways like we're seeing here. So provide a molecular explanation for the dependence of rate on concentrations of the reactants. In other words, why does this reaction get slower with time? Why does my reaction rate sort of taper off and then level off? Why does it start out fast and get slower? Why does concentration affect rate? Okay. So we would say then that having more, and you can phrase these as you know a lot of ways, more reactant particles present, in other words, a higher molarity, in this case of PCl3 and or really Cl2, will allow for more collisions, or more frequent collisions. Sometimes you'll hear greater probability of collisions, or frequent collisions between PCl3 and Cl2. And you want to be specific, but collisions of what type? Between PCl3 and another PCl3? That doesn't do anything. Between PCl3 and a PCl5? That doesn't do anything. Between PCl3 and the walls of the container? That's how we measure pressure, PCl3, but that's not going to cause a reaction or have any influence on the rate. So collisions between PCl3 and Cl2. Okay. And therefore, faster reaction rate. That'd probably be enough, right? We related the idea of concentration or molarity to collisions and rate. And that's the idea. We're talking about particles at a molecular level. You could say reactant molecules. They're not going to slice and dice that sort of noun choice. Particles is a good generic term to use because it covers atoms, ions, molecules, all the different sorts of flavors of particles. under one umbrella. For D, it wants us to provide a molecular explanation for the dependence of rate on temperature. So why would temperature have an influence? Well, that doesn't change the number of particles present, right? Raising the temperature doesn't change the number of particles. It doesn't change the concentration of the reactants, but it does make them all move faster, right? So we could say that increasing temp will increase the kinetic energy, which we can sort of translate as velocity, right, of the reactant particles. Right? That's what kinetic energy is, velocity. It's based on velocity of the particles. And temperature is average kinetic energy. So raising temperature raises kinetic energy, which we would sort of think about as velocity. And yield, or bring about, or cause, whatever verb you like, and yield more collisions. And here's the key, with sufficient energy to exceed the activation energy barrier. And we want to remember that we have this idea of an activation energy at all times. Why does raising temperature make it possible for a reaction to happen? Why does cookie dough bake at 350 in my oven but not at 200? It just kind of melts into a puddle. It doesn't brown up. The reaction that I'm trying to have happen in my cookie dough, right, doesn't occur until I reach a certain activation energy. It won't brown at room temperature on my counter. It certainly won't brown in my refrigerator. But if I get to that 350 temperature, that's a temperature that we know works, right? And we remember that has to do with our graph that we often see in terms of kinetics. We don't know if it's exo or endothermic here, but there's that activation energy that has to be exceeded. And then if it's endothermic or exothermic, we finish the curve, appropriately. But there's that activation energy that has to be achieved. And if you increase the velocity, you'll have more particles that are able to exceed that activation energy and kind of get over the hump to become products. All right. So that's that question. Got a lot of things going on there, some ratios. We've got a little bit of whether we know it or not, mole ratios, and almost some stoichiometry. Helps to be thinking about a rice table, even though they didn't ask you to do any calculations with a rice table. It helps to have that as sort of a tool in your mental toolbox, because then you might remember that ratio of 1 to 1 to 1 comes through and is not so much as a rice table, but shows up here in the graphs and how the different paths on my graph are sort of reflected of each other. The way that they are changing, all three of those substances are changing, is a function of the fact that they're all 1 to 1 to 1. So the amount that they changed with time is the same amount for each of them. It looks like they all went down or up by about 0.6 or 0.7 moles, something like that. And so those changes were consistent. All right, so that's about 22 minutes. I'm going to stop this video there. We'll do a couple of questions in another video here in just a moment. We'll pick it up with number 3. Hopefully that was helpful for you. If you have questions on these or any other of the problems in the free response packet, feel free to make a note of what those questions are and contact me as soon as you get a chance. Thanks for listening. See you next time.